Lighthouse Scientific Education presents a lecture in the Solutions and Water series. The topic, concentration and dilution. The lecture can be viewed in its entirety or search for particular concentration scales or dilution problems. Material in this lecture relies on an understanding of the previous lectures, solutions and solubility, and molarity, molality, and mole fraction. The lecture begins with some basic definitions and accompanying equations. Some of the more common concentration scales or ratios are discussed, including percent concentration, that is mass to volume ratio, percent concentration mass to mass, percent concentration of volume to volume ratio, and parts per million or billion. Those are extended into concentrations as a conversion factor. Example problems of conversions are offered, as well as an example of preparing a solution in a lab setting. The second part of the lecture is given over to dilutions. Dilutions can be summed up with the equation C1V1 equals C2V2. This is shown with example dilution problems. An all-important topic in chemistry is concentration. We will focus the discussion in this lecture on the concentration of solutions with a liquid solvent. Some extension into gas solutions can be made from this discussion. Let's start with a review of solutions. Some compounds dissolve or dissociate in liquids and form solutions. The dissolved compound is called the solute, and the dissolving liquid is the solvent. The amount of solute per volume of solution, or in some cases the amount of solvent, is called the concentration. Concentration is a ratio or a fraction. The numerator is always the amount of solute, but depending on the scale, the denominator is usually the amount of solution or solvent. The concentration scales covered in this lecture will differ by the units for the solute, solvent, and solution. There are a couple qualitative descriptions most people are aware of. A dilute solution is where there's a small amount of solute, and a concentrated solution is where there's a large amount of solute. Diluted and concentration are usually condition dependent and are not absolutes. Giving some values to concentration, if 3.5 grams of NaCl is dissolved in 1.0 liters of water, then the concentration can be described as the amount of solute, 3.5 grams, over the amount of solvent, 1 liter. An all-important note can be made here. If the amount of solute is small compared to the amount of solvent, then the volume of solution is approximately equal to the volume of the solvent. This only works with very dilute solutions, but it allows us to write a second ratio with volume of solution in the denominator. These two concentrations are approximately equal since this is a very dilute solution. As for units, this concentration scale is grams over liters. It is mass or weight to volume scale. Concentration is a three-variable equation. In the previous example, those three variables were concentration, mass or weight of solute, and volume of solution or solvent. If we stop to think about it, we've seen a similar set of three variables. It is the density with its mass to volume ratio. The variable d equals the variable m over the variable v. A direct comparison of the equations shows just how similar they are. The point here is that the study of concentration can be built upon the study of density. Concentration problems using this equation can be solved in the same manner as the three-variable density problems. Later on in the lecture, we will explore this process in more detail. With the basic form of concentration scale in hand, we can move into specific scales. Notice that the definition of concentration does not explicitly say what the units are for the solute, solvent, or solution. That is where the different concentration scales vary. We've already covered concentration scales that use moles as the unit of the solute. There are three common mole-based concentration scales, and they are discussed in detail in the molarity, molality, and mole fraction lecture in the mole series. We will briefly cover them here. The first and most important is molarity, units given as capital M. This scale is the number of moles of solute dissolved in 1 liter of solution. Capital M means moles per liter. A second and less frequent used scale is molality. Units are given as small m. It is the number of moles of solute per kilogram of solvent. Little m means moles per kilogram. Molality plays a prominent role in the colligative properties lecture. The final scale is mole fraction. Its unit is the lower Greek letter chi. Mole fraction is the moles of solute over the total moles of solution. That is as much as we're going to cover in this lecture of the mole-based scales. What we will cover in depth are scales in which the amount of solute, solvent, and solution are given in mass or volume. The most common of these types of concentrations is the percent concentration scales. 3 versions will be presented here. The first is percent concentration with the ratio of mass or weight grams of solute per volume mil of solution. Since it is a percent, the ratio of weight per volume is multiplied by 100. A second weight percent concentration is as mass or weight grams of solute per mass or weight grams or kilograms of solution. It is a weight per weight scale and also multiplied by 100. A final way to present percent concentration is volume mil of solute per volume mil of solution. It is a volume per volume scale and is also multiplied by 100. There are 3 representations of percent concentration because there are 3 combinations of weight or volume for solute and solution. The one new scale covered here that is not a percent concentration is parts per million or parts per billion. Often these scales are mass grams of solute per mass grams of solution. Like the percent concentration, this ratio is multiplied by a large number. The numbers are, however, very large, 10 to the 6th, 1 million, or 10 to the 9th, 1 billion. Let's spend some time with each one of these 4 scales and show some sample calculations. Starting with the first percent concentration scale, mass or weight to volume. Often weight to volume is designated by W over V. This calculation of percent concentration will have the mass or weight of the solute divided by the volume of the solution and multiplied by 100 to get percent. An example of such a solution is the 5% weight to volume NaCl. The solvent of water is implied here. A couple of example problems of calculating this type of concentration will be helpful. Keeping the concentration formula handy, what is the percent concentration weight to volume of a 100 ml solution that contains 10 grams of NaCl? Do we know if this is a concentration problem? Well, it is a concentration problem, and it looks like it is the percent concentration with a solid solute dissolved in a liquid solvent. It is a mass or weight to volume concentration. The solvent type is not mentioned here, so it is implied to be water. Inserting the problem values into the percent concentration W to V equation has a weight of 10 grams for the solute, sodium chloride, and a volume of 100 ml for the solution. The equation is complete when the ratio is multiplied by 100. That is because this is a percent concentration, and percent means per 100. The math comes to a 10% weight to volume NaCl solution. Is the percent sign required in this concentration? Yes, it is. It lets a person know that the 10 per 100 is really a 1/10 solution. Since we have this problem up and solved, we can tweak the problem to cover variation that comes up regarding units, which will require an additional step. Say that instead of being given 100 ml of solution, the problem offered 0.100 liters. The problem can be solved the exact same way if liters are converted into milliliters. The given units are 0.100 liters, and using the metric conversion into milliliters, oriented to cancel liters, will produce the desired units of mils, 100 of them. Yes, this is the same value as the original problem, so the conversion will be the same 10% weight to volume NaCl solution. What this tweak to the original problem highlights, aside from the need of a metric conversion, is that if the liter value is inserted directly into the percent concentration equation, instead of an equivalent milliliter value, a very different concentration will come out from the math, even though the liter and milliliter volumes are the same. This given definition of percent concentration specifically calls for milliliter, and that is what it should get. A second practice problem with this concentration scale says that a solution is formed by the addition of 25.0 grams of ammonium nitrate to water, making a final volume of 0.150 liters. What is the percent concentration, weight to volume? In scouring the problem, it can be seen that the units of the solute and solvent are weight and volume respectively, just as the problem asks for in the concentration scale. However, the weight is given in kilograms, but the definition calls for grams. This requires a metric conversion, with the conversion factor in the proper orientation to cancel out kilograms and to convert 0.025 kilograms to 25 grams. Now applying the definition, 25.0 grams of ammonium nitrate divided by 150 mils of solution times 100 is 16.7% weight to volume ammonium nitrate. On to the next scale, and it is percent concentration, mass to mass. It is usually called weight to weight. It is weight in grams of solute per weight in grams of solution. To get percent, the ratio is multiplied by 100. Units are grams per gram. The calculation for percent concentration, weight per weight, starts with the weight of the solute over the weight of the solution times 100. This ratio can actually be expressed in a manner that is more conducive to solution preparation. Remember, the solution is really the combination of solute and solvent. So the weight of the solution is the sum of the weight of the solute and the weight of the solvent. This is a more detailed way of describing the scale. Unless, of course, there's more than one type of solute in the solution. While the addition of the other solute makes the equation look more difficult, all it really does is change the denominator by adding a second solute, since the weight of the solution is the weight of all the components in the solution. One other point to make that will help reduce the overall confusion. Most of the time, liquid solvents are measured by volume. Maybe a graduated cylinder is used. However, with this scale, weight is needed. There's a convenient way, though, to still use volume if the solvent is water and its temperature is near room temperature. That is taking advantage of the one-to-one relationship between water's weight and volume. 1.00 ml of water is 1.00 gram of water. This comes from the density of water near room temperature. It is 1 gram per mil, so 25 ml of water is 25 grams of water. 1,000 ml or 1.00 liter of water is 1,000 grams of water. Okay, keeping this equation for percent concentration, weight to weight, let's do an example calculation. 37.0 grams of HCl is dissolved in 63.0 grams of water. What is the percent concentration, weight to weight, of HCl? An examination of the problem shows a weight for the solute and a weight for the solvent. The equation for percent concentration, weight to weight, has the weight of the solute over the weight of the solution. But we're not given the weight or volume of the solution. Or are we? Isn't the solution in this problem really just the sum of the solute and the solvent? Adding their weights together gives a weight of the solution as 100 grams. That value can be directly added to the percent concentration equation, as can the sum of the solute and solvent. We will use that description of the weight of the solution because it will be useful in making a separate point later in the problem. Both ways work. The final step in the setup of the equation is to multiply by 100. A bit of calculator work has a final answer of 37.0% weight by weight HCl. This is our third concentration calculation problem, and the process should start to feel more comfortable. One component that may add confusion to a problem like this is if the solvent water is given in units of volume instead of weight, as asked for in the concentration scale. What's to be done? Well, fortunately, we know a direct relationship between the volume of water and its weight at room temperature. At this temperature, it is pretty much a one-to-one relationship. 63 mils is equivalent to 63 grams of water. That was the gram amount in the original problem. It can be directly inserted into the percent concentration equation as written and solved to the same concentration. All right, one last twist with this problem. How would the concentration of HCl change if the HCl and the water contributions are left as they are, but an additional solute was added? 5.00 grams of sodium iodide will also be dissolved in this solvent. We can call the sodium iodide solute 2. Earlier we saw that an additional component to the solution predominantly affects the denominator of the equation, because the solution is the sum of all its components. Unless the solutes have common chemicals, there will be no change to the numerator. Essentially, this new problem is solved the same way as the previous one. The equation begins with the weight of the solute HCl. If the question asks for the concentration of sodium iodide, its 5.00 grams would need to be added here instead. The denominator of the equation has the weights of both solutes and the solvent. The full weight of the solution is 37.0 plus 5.00 plus 63.0 for a value of 105 grams. This weight can be substituted into the equation for ease of viewing. Multiply the ratio by 100, gives a concentration of the HCl as 35.2% weight to weight. This concentration is less than the concentration without the additional solute, but that is to be expected because the volume of solution is larger with the addition of a second solute. The last of the percent concentration scales is the volume to volume one. That is the mil of solute per mil of solution, and the percent says multiply by 100. A real-world example of this concentration scale is with alcohol beverages. Wine is about 12% volume per volume ethanol. All alcohol containers will provide this concentration scale of ethyl alcohol. Solution preparation using this scale is a common practice in chemistry labs. There are two ways to prepare a solution using percent concentration, volume to volume. They share the first step. Measure out the volume of solute. The first method and the more common method is to add solvent to the solute until the final volume of solution is met. A second method is to separately measure out the calculated amount of solvent. The solute and solvent are combined. The underlying principle here is that the volume of solution is the same as the volume of solute plus the volume of solvent. This is the same argument that we used with weight of solution being the sum of the weights of the solute and the solvent. The equation for percent concentration, volume to volume, has the volume of the solute over the sum of the volume of the solute and solvent. Multiplication by 100 follows. For more dilute solutions, the solution volume is the volume of the solute plus the volume of the solvent. Sometimes, and often with concentrated solutions, the sum of the volume of the solute plus the volume of the solvent does not equal the volume of the solution. That is seen when 30 mils of propanol is added to 70 mils of water. The mixture does not equal 100 mils. It's an intermolecular interaction thing, and such changes in volume cannot be predicted in advance. To be safe, for more concentrated solutions, it's probably best to change the denominator of the ratio back to volume of solution. When solving textbook problems, using this scale in either form of the denominator will usually be acceptable. In fact, we will take that first form of the equation with the sum volumes into the example problem. 7.5 mils of isopropyl alcohol C3H7OH is added to 142.5 mils of water. What is the percent concentration, volume to volume, of the isopropyl alcohol? This is the concentration problem of the volume to volume kind because it is a liquid solute dissolved in a liquid solvent. Calling up the concentration equation, in the numerator, the solute volume is added, and in the denominator, the sum of the volumes of the solute and solvent are placed. Pulling the values of the denominator out, we see that it solves to a tidy value of 150 ml. Placing the volume of the solution in the denominator and multiplying by 100 gives a concentration of 5.0% volume to volume C3H7OH. That is a relatively dilute concentration. This exact problem could have been reworded with the water added to a final volume of 150 ml, and it would yield the exact same concentration. The volume of the solution can be given outright or summed from the solute and the solvent. The last type of concentration scale is the parts per million ppm or parts per billion ppb. These scales are most often used in environmental measurements, including those of the soil and atmosphere. They are a mass-to-mass scale, with the solute and the solvent being given in the same unit denomination, both in grams, for example. The scales are similar to the percent concentration in that the ratio of solute to solvent is multiplied by a large number. For the part per million, the ratio is multiplied by 1,000,000, 10 to the 6th. And for parts per billion, the ratio is multiplied by 1,000,000,000, 10 to the 9th. The equation for ppm and ppb will look a lot like the percent concentration in the weight-to-weight scale. The weight of the solute over the weight of the solution times 1,000,000 or billion, depending on the scale. There's an important shortcut in dealing with the very small amount of solute found with the ppm and the ppb scales. When the solute is a tiny fraction of the solution, the weight of the solvent is approximately equal to the weight of the solution. The equation can be modified to acknowledge this without much a change in the actual concentration value. Keeping the concentration equation and bringing up an example problem, 0.0080 grams of oxygen, O2, in the gas phase is dissolved in 1,000 ml of H2O, liquid phase, at 22 degrees Celsius. What is the ppm and ppb of O2? There are two issues regarding the solvent water. The first is that it is given in volume units of mils, but the concentration scales want weight in the same unit as the solute, grams. We've seen this before. It is handled by making the equivalent statement of 1,000 mils of water equals 1,000 grams of water at 22 degrees Celsius. That is based on the density of water at room temperature. The second issue is that, as written, the ppm and ppb equation asks for the weight of the solution and not the weight of the solvent. That too was addressed earlier. Since the solute makes up such a small part of the weight of the solution, it is acceptable for the weight of the solvent to be used in place of the weight of the solution. Now we are ready to tackle this problem. Beginning with the parts per million calculation. The weight of the oxygen is in the numerator, and the weight of the solvent is in the denominator. Multiplying this ratio by 1,000,000 gives a final value of 8.0 parts per million of oxygen. The scale is an appropriate one because the numerical value is in a comfortable range. Contrast that with the parts per billion. It has the same ratio, but is multiplied by a larger number, 1,000,000,000. It yields a value of 8.0 times 10 to the 3 ppb oxygen. Given the two, which one would you rather deal with? The choice of concentration scale is driven by the ratio. The smaller it is, the bigger the number it is multiplied to get a value in a comfortable range, between 1 and 10 if possible. That is our coverage of concentration scales. I said earlier, concentration is a 3-variable equation that when given 2 of the variables, the third can be solved for. That is, concentration can be used to move between mass of the solutes and volume of the solution, or the solvent in some cases. There's one point that needs to be made clear before proceeding to the setup for conversions. Only the ratio of solute to solution is used in a conversion. If percent concentration is given, it needs to be multiplied by 100 to remove percent. A ppm value will need to be multiplied by 1 million, and a ppb will need to be multiplied by 1 billion in order to just return the solute to solution ratio. A very similar description of concentration as a conversion factor is given in the study of molarity in the molarity, molality, and mole fraction lecture. Converting between moles of solute and liters of solution is probably the most common of these types of conversions. Be sure to review these transitions in that lecture. For demonstration purposes, we will return to our basic setup for conversions that has the current units for the given units of a conversion and desired units for the wanted or asked for units. If we were given values in liters of solution and asked for mass of solute, we can use the concentration of the solution as a conversion factor. That is, the concentration is written with solute over solution. Liters cancel out, and units of mass remain. Flipping the problem around, with the mass of the solute as the given and volume of solution as the asked for units, would require a flip of the concentration scale, volume in the numerator and mass in the denominator, so that it cancels out. This should be a common conversion setup for the student at this point in their study. Still, an example problem couldn't hurt. 0.22 liters of a 10 gram per liter magnesium chloride solution has how many grams of magnesium chloride? Is this a conversion problem? It is, because it is asking for a different way, different units, to express the same value of the same solution. Begin the problem with the setup for the conversion. The current or given units is the 0.22 liters of solution, and the desired or asked for units is the mass of the solute. Is there a known conversion that relates liters of solution with the amount of solute in that volume? Yes, the concentration, as written in weight over volume. Is the orientation of the concentration correct? Would flipping the fraction be a better fit for the setup? No. This orientation allows for the canceling out of the given units, leaving the desired units of mass. A bit of calculator work has the mass at 2.2 grams of magnesium chloride. It is given to two significant figures because the concentration scale is only given to 2 sig figs. That was not too bad. But what if the original problem was not giving in liters of solution, but in milliliters of solution? It is still the same overall problem, but there's a new issue in that the concentration scale and the given value are not in the same magnitude. To use the concentration scale as a conversion, the given units will need to be in liters. What can be done about this? A separate metric conversion is needed. The 220 mils need to be converted into liters of solution. That conversion factor, of course, is 1 liter over 1,000 mil, with mil in the denominator so that the given units cancel. The math has the conversion as 0.22 liters of solution. And yes, it is the same value as in the original problem, which means that the same conversion can be used and the same 2.2 grams of solute will be obtained. To give additional perspective to the conversion problem, a second example is given. 5.50 grams of KMnO4 is added to an empty flask. To make a 20.0 gram per liter potassium permanganate solution, what volume should the flask be filled to? Is this another conversion problem? Yes, since what we are asking for is relating the amount of solute to the amount of solution. The setup starts with the given grams of potassium manganate and asks for the desired units of volume of solution. As with the previous example, the concentration serves as a conversion factor. Is this the correct orientation of the concentration? Do given units of grams cancel out? No, they do not. A flip of the concentration is needed. Grams of potassium permanganate have to be in the denominator to cancel out with the given units of grams. The division of 5.50 by 20.0 gives a volume of 0.275 liters. Another way of saying that is 275 mils. Being able to make this kind of transition between mils and liters is a useful skill. These types of conversions are not only necessary for homework and testing problems, they also come up in a lab setting. Students can be asked to prepare a solution for a lab. That solution will have a set concentration and a final volume. For example, the student might be asked to prepare 0.20 liters of a 25 gram KCl per liter solution. It's an aqueous solution. How should they go about this? Step 1 is to calculate the appropriate mass of solute from the concentration and solution volume. It is the only piece of information not given and will be solved for in the same manner as the previous conversion problems. Given units of 0.20 liters, concentration oriented to cancel liters, yielding a value of 5.0 grams of KCl. With this piece of information, weigh out the calculated mass of solute, 2.5 grams. The second step is to add the solute to an empty graduated cylinder or volumetric flask. Be sure that as much of the weighed out solution as possible finds its way into the vessel. A stir bar can be added here if the solution is on a stir plate. Finally, add solvent, water in this case, until the final volume is reached. Stirring is advised. This is a straightforward process, but focus is needed to prevent errors that may or may not be easily detected. That completes our concentration portion of the lecture. The next section deals with dilutions. Solutions are not only common in lab, they are common in everyday life. Dilution is the act of reducing the concentration of a solute in a solution. In practice, that generally means to add more solvent without adding more solute. In every instance, the concentration of the solute is lower in the dilution. Examples that we are familiar with include making orange juice by adding 4 cans of water to frozen orange juice concentrate. Dilutions can come up in art when a darker color is made lighter. In each case, the dilution results in a weaker product. Looking at the practice of making a dilution from a more mathematical perspective, the amount of solute is constant, but the amount of solvent is increased. Say we have a concentration where X grams of some solute is dissolved in Y mils of some solvent. Dilution occurs with the addition of more solvent. We will call that additional amount Z mils. Looking at a concentration ratio after the dilution shows that the denominator is larger due to the addition of solvent. From a fraction view, a larger denominator produces a smaller fraction, or a smaller concentration in our case. While dilutions can initially seem confusing, dilution problems are almost all solved the same way. Fortunately, there's an equation that relates the concentration of a solute before and after a dilution. It works with a concentration that has volume of solution in the denominator and the solute in the numerator having units of mass or count. That includes concentration with weight for the solute like mgs per mil or grams per liter. Also percent concentration, the weight to volume kind. And the molarity scale, moles per liter, with moles being a unit of count. The key is that the concentration be given with volume in the solution. So what is the magical equation that relates the concentration of a solute before and after dilution? Simply, C1V1 equals C2V2. The 1 subscript designates values from before the dilution, and the subscript 2 designates values after the dilution. Initial and final work as well. C stands for concentration. C1 is the initial concentration of the solute before the dilution. V stands for volume. V1 is the initial volume of the solution before the dilution. C2 is the final concentration of the solute after the dilution. And V2 is the final volume of solution after the dilution. As a heads up, sometimes the C1V1 equals C2V2 equation is written with M's in place of the C's. It just means that the concentration scale being used is molarity. Nothing else has changed, including the process of solving dilution problems. Dilution problems are tackled step by step and do well with a problem-solving strategy. On first encountering a problem, take the time to identify the known and unknown variables. For dilution problems, those terms will generally be the concentration and volume values of before and after the dilution. In the vast majority of dilution problems, the student is given 3 of the 4 variables in the dilution equation and asked to solve for the 4th. The second step is to find the relationship between the known and unknown variables and to solve that relationship mathematically. That is, solve the equation for the unknown variable. In this example, C2 is the unknown variable, but it is not isolated by itself on one side of the equation. This type of equation, however, solves with a single algebra step. When an equation only having multiplication, the unknown variable can be isolated by dividing both sides of the equation by the variable that is the neighbor of the unknown. In this example, the unknown is C2, and its neighbor is V2. Divide both sides of the equation by V2. The V2's on the right-hand side of the equation cancel out, leaving the unknown variable isolated. The equation is algebraically solved. The last step is to take the equation and input the numerical values from the setup and solve the math. It's always a good idea to keep an eye on the units to make sure the final solution has the same units as the unknown variable. Let's put the process to the test. Calculate how many mils of 1.0 molar HCl is required to make 100 mils of a 0.1 molar solution of HCl. This is one of the problems that uses molarity as a concentration scale. Begin with the setup. What is known and not known in this problem? Well, there appears to be 2 concentrations, a 1.0 molar and a 0.1 molar. Which one is the before or initial concentration and which one is the after or final concentration? Remember, dilution always reduces the concentration. So the 0.10 molar, which is less, is the after dilution concentration. This brings up the first helpful hint in solving dilution problems. C1 is always bigger than C2, and V1 is always smaller than V2. We can add the smaller concentration to C2 and the larger to C1. What about volume? There is 100 mil. Which concentration is it attached to, C1 or C2? Yes, it is C2. So we add the value to V2. All that is left is V1. Is its value given? No, it is what the problem asks for. A question mark designates it as an unknown. On to step 2, finding the relationship between the known and unknown variables. It is, of course, the topic equation C1V1 equals C2V2. The similar equation M1V1 equals M2V2 could also be used here since concentration is in molarity. Also part of step 2 is to solve the relationship in terms of the unknown. Is this equation solved for V1? It is not. Some algebra is necessary, and it is the same algebra for every dilution problem. To isolate the unknown variable, divide both sides of the equation by the variable that is the neighbor of the unknown. The variable next to V1 is C1. Divide both sides of the equation by C1. On the left-hand side of the equation, the C1s cancel out, leaving just the unknown variable, V1. The equation is considered algebraically solved. The student may ask, why not just input the variables into C1V1 equals C2V2 equation? The answer is that adding numbers and units complicates the original equation and increases the likelihood of math errors. solving the equation with the variables in place is a best practice. Step 3 is to solve the equation mathematically. Add numerical values from the setup into the equation. C2 is 0.10 molar. V2 is 100 mils. C1 is 1.0 molar. The unit of molar HCl cancels out, leaving mil units, which is a good thing since we are solving for a volume. Some calculated work gives us a volume for V1 of 10 mils. 10 mils of a 1.0 molar solution diluted to a final value of 1.0 liters will have a concentration of 0.1 molar. Onto a second problem, and it will be solved in a nearly identical manner. Almost. 100 mils of water was added to 150 mils of a 70% ethanol solution. What is the new concentration? The solution to the problem begins with the setup. Looking at the problem, we see a volume attached to a concentration. Hint number 2 says to connect a volume to its concentration. If that is done for one pair, the before pair or the after pair, then the other values have to belong to the other pair. The 150 mils belongs to the 70% concentration. The question to ask is whether this pair represents before dilution or after. A careful reading of the problem shows the water is added to this solution. These are the before dilution values. Add them to the V1 and C1 in the setup. Note that the ethanol is shortened to ETOH. The OH is the alcohol part. There are still two variables to deal with. The question asks for the new concentration, so clearly C2 is an unknown. And the volume V2? Is this unknown? Is it that 100 mils? Well, it might initially seem that way, but the volume of the dilution cannot be smaller than the starting volume since solvent is added. Hint 1 says V1 is smaller than V2. Are we stuck? Perhaps a revisit to the problem would help. It says that the 100 mils is added to the 150 mils of the 70% concentration. So the final volume, V2, will include the 150 mils of V1 plus the addition of 100 mils. V2 is 250 mils. V2 is larger than V1. This leads to hint 3. V2 is equal to V1 plus added solvent. Sometimes the problem will give the whole volume of V2, and sometimes its value is implied by giving V1 and the amount of additional solvent. Now we're ready for the relationship expression that connects the known and unknown values. It is of course C1V1 equals C2V2. Is the equation solved for the unknown C2? No, it isn't. We can employ the same strategy in isolating C2 as we did in isolating V1 in the previous problem. That is, divide both sides of the equation by the variable next to the unknown. The variable next to C2 is V2. Divide both sides of the equation by V2 and cancel that variable out, leaving C2 isolated on one side of the equation. It doesn't matter which side. The equation is algebraically solved, and we are ready to insert the numerical values from the setup into the equation and solve. The initial concentration times the initial volume divided by the final volume. The unit mils cancel out, and the math gives a diluted concentration of 42% ethanol. The last example asks for what is the final volume when 250 mils of a 1.5 molar NaCl solution is diluted down to a concentration of 0.25 molar. This is a typical type of question one asks when making a dilution from a concentrate. Starting with the setup and analyzing the problem, one thing that stands out in our reading of the problem is a paired or connected concentration and volume. Hint number 2. Is this the initial or final pair? Well, noting that the other concentration, 0.25 molar, is smaller than the 1.5 molar in this pair, it is safe to say that the 1.5 molar is the initial concentration. Hint number 1 says C1 is bigger than C2. This pair can be added to the setup as C1 and V1. The remaining values in the problem include the final concentration, C2 is 0.25 molar, and an unknown final volume. V2s are unknown. What relates the known and unknown values? The C1V1 equals C2V2 equation. And like the previous problems, it is not solved for the unknown. And like the previous problems, the unknown is isolated by dividing both sides by its neighbor in this problem, C2. When both sides are divided by C2, the C2s on the right-hand side of the equation cancel out. The unknown is algebraically isolated. Step 3 is the plug-and-chug part. Insert the values from the setup, C1, V1, V2. Cancel units and do the math. 1.50 times 250 divided by 0.25 is 1,500 mils. Some metric converting, and that comes to 1.500 liters. Dilute 250 mils to 1,500 mils, and the concentration will drop from 1.5 molar to 0.25 molar. And that concludes the material for this lecture. Our recap: some compounds dissolve in liquids and form solutions. The dissolved compound is the solute, and the dissolving compound is the solvent. The amount of solute per volume of solution, or amount of solute per volume of solvent, is called the concentration. We covered 4 concentration scales in this lecture. Percent concentration, weight to volume, has the solute in units of mass or weight and the solution in volume units. The ratio is multiplied by 100. Percent concentration, weight to weight, has the solute and the solution in units of weight. The ratio is multiplied by 100. Percent concentration, volume to volume, has the solute and the solution in units of volume. The ratio is multiplied by 100. Parts per million or billion has the solute in units of mass and the solution in units of mass. The ratio is multiplied by 1 million for ppm and 1 billion for ppb. Concentration is a ratio and can be used to move between units of the solute and units of the volume of the solution. Dilution is the act of reducing the concentration of a solute. Add more solvent without adding more solute. The equation C1V1 equals C2V2 relates the concentration of a solute before and after a dilution. The 3-step problem-solving technique fits well with solving dilution problems. And that concludes our lecture. Concentration and dilution are fundamental components of chemistry.